In general, consider an equation AA plus BB giving product. The rate of the reaction depends on, that is by experimental data. Rate can be written as rate is equal to K into concentration of A raised to the power P, concentration of B raised to the power Q, where P and Q may or may not be same as the stoichiometric coefficient of A and B present in the balanced equation of the reaction. The rate law of some reactions, for example, 2NO plus 2H2 giving N2 plus 2 water molecule. In that, the rate is found to be equal to K into NO raised to the power 2. But for hydrogen, as in the stoichiometric factor, no power is there. That is only raised to the power 1. Now 2, hydrogen combines with iodine and forms 2 hydrogen iodide. In this, the stoichiometric factor is for hydrogen and iodine is 1. Therefore, in the rate equation, experimental data also, they are getting the same value. That is hydrogen, only the power is only 1, and iodine, the power is only 1. That means this first example shows that the stoichiometric factor are not in agreement with the experimental fact. But the second reaction shows that the stoichiometric factor are in agreement with the experimental fact. That is the result. There are other 5 examples are given in page number 212 in the textbook. Please refer and see which are the chemical reaction is in agreement with the experimental data, the stoichiometric factors given in the chemical equation, and which are not in agreement with the experimental result with the stoichiometric factors of the balanced equation. Next point is rate constant or specific reaction rate. The constant K appearing in the expression for rate law of the reaction is called rate constant or velocity constant. It is also referred to as specific reaction rate. Let us consider the following reaction. The same reaction, general reaction, which we already considered. That means AA plus BB plus CC giving product. Suppose the rate law is given by, that is by experimental determination, we determined P, Q and R. Rate is equal to K into A raised to the power P, B raised to the power Q, C raised to the power R, where K is the rate constant. This K is known as the rate constant, and the powers P, Q, R represents the dependence of the reaction rate on the concentration of the reactants A, B and C respectively. If the concentration of each of the following is unity, we are going to consider that concentration of A is equal to 1 moles per liter, concentration of B is equal to 1 moles per liter, and concentration of C is equal to 1 moles per liter. In that case, rate is equal to K. Therefore, we can define rate in another way. Thus, rate constant may be defined as given below. The rate constant of a reaction is equal to the rate of reaction when the concentration of each reactant is unity. That means if all these are concentrations are equal to 1, then rate is equal to K. The rate constant of a reaction has a definite value at a particular temperature. It does not depend on the initial concentration of the reactants. Its value increases with increase in temperature. Fill in the blank question. Units of rate constant. The unit of rate constant depend upon the overall sum of the powers of which the concentration of the reactants have been raised in the rate law. Therefore, we have to find out what is the unit, how you are arriving at the unit of the rate constant. Therefore, let us take an example and we'll derive a small equation.